So we have a tennis ball may leave the racket of a top player on a serve with a speed of 65 meters per second. Right? So let's say we have a tennis ball here, okay? And this tennis ball, it leaves so it leaves the tennis racket, right? So here's a tennis racket. So this is my old wooden racket from Wimbledon days, you know. All right. So when it leaves the tennis racket, this thing is coming out with initial velocity of this tennis ball is 0. When you hit this thing with a racket, this thing is at 0 meters per second. But when you hit it, your final velocity happens to be 65 meters per second, right? 65 meters per second. Therefore, as this thing is leaving the racket, is going off at this initial velocity for the tennis ball is 0. Okay? The mass of the tennis ball is 0.0600 kilograms, right? And the time that the tennis ball and the racket stays in contact happens to be 0.0300 seconds. Okay? They want us to figure out what is the average force, right, on the ball. Well, we know average force is equal to the impulse divided by delta t, right? And since average force then is equal to, right, momentum final minus the momentum initial over delta t. We said initial momentum is 0 because the velocity of the tennis ball is 0. So this goes to 0. Okay? Therefore, the force average then is equal to mv final over delta t. And that is 0.0600 times velocity is 65, final velocity is 65 meters per second. Divide that by delta t, which happens to be 0.0300 seconds. All right, so if you work it out, my force average comes out to 130 newtons. And if you want, you could say in the positive x-hat direction, right? Because it is a vector, and force is a vector, so you could do it that way. Okay? All right. Any questions so far? All right, good. What about for part B then? For part B, they're asking, would this force be large enough to lift a 60-kilogram person? Well, in order to lift a 60-kilogram person, right, you're going to need pretty much the same amount of force of Fg in the opposite direction, like so, right? The force applied has to be minimum of Fg, right? So force applied has to be same as mg. So if force required to lift a 60 kilogram person comes out to 60 times 9.8, which comes out to, it looks like 588 newtons is required to lift the person of 60 kilogram mass. Well, we only have 130 newtons here. So the answer is no friggin' way, right? Right? No way. All right? Hopefully that's obvious. All right. We'll leave that up there for now. All right, then a golf ball, number 9, a golf ball of mass 0.045 kilograms is hit off the tee at a speed of 45 meters per second. The golf club was in contact with the ball for 5,000th of a second, which is 5.0 times 10 to the negative third, right? 5,000th of a second. Find A, the impulse imparted to the golf ball, and B, the average force exerted on the ball by the golf club. All right? So, well, if we were to visualize this, so here's golf. So here's the golf ball, right? They're the dimples, right? And a golf club comes down and whacks this thing, right? So here's the golf club. Right? Coming down to whack this golf ball, right? Therefore, what's going on? Well, we know the initial velocity of the golf ball is equal to 0 because golf balls are at rest when you're hitting that thing, right? So what happens after it gets whacked? Well, the golf ball final velocity, right, VF, happens to be 45 meters per second. The mass of the golf ball happens to be 0.045 kilograms. The time the golf ball and the club stays in contact happens to be 5,000th of a second. Okay, 5 milliseconds. So these are pretty much what's given to us for this problem. So let's figure out what's going on. Okay? And all right. So here they want us to figure out what impulse is imparted to the golf ball. So for part A, impulse is simply nothing more than just change in momentum. And change in momentum happens to be momentum final minus the momentum initial. And that is equal to mv final minus mv initial. So mass is 0.045 kilograms. V final is 45 meters per second minus m times vi. Initial velocity is 0, so this whole term just goes to 0. So my impulse, or simply change in momentum, happens to be 2.025 kilograms times meters per second. I guess you could put Exerted down if you want to, right? So this is the impulse the club has imparted onto the golf ball. Okay? All right. Now, what about part B? Part B asks, what's the average force exerted on the ball by the club, right? So for part B, the force average is equal to delta P over delta T, right? Therefore, force average is equal to delta P, which is 2. We already calculated that here, right? So 2.025, divide that by delta T, which is 5.0 times 10 to the negative third seconds. Right. So this is kilograms, meters per second, and this is seconds. So your force average comes out to, well, the Exerted direction, I guess, if you want. Right. It comes out to, I think you get something like 405 newtons Exerted. That's pretty significant, huh? That's pretty significant. So, because the contact time is so small, you would have to apply this much of force in order to make the golf ball travel at 45 meters per second. However, for a tennis ball, your contact time is a lot bigger. This is 300th of a second, where this is 5,000th of a second. So in order to make the tennis ball, which is heavier, right, travel at 65 meters per second, because the contact time is so much longer than this, you only need 130 newtons of force to make your tennis ball go at 65 meters per second. Where the golf ball, which is, a little less than tennis ball, but still, it requires 405 newtons to go at 45 meters per second because your contact time was less. That's why your following through with your swing really helps to increase that contact time. Okay, so that's why your coaches will always tell you, follow through with your swing. Okay? Alrighty. Any questions so far? Okay, good. I'll leave this up here for about a minute so you guys can copy it down. All right. Now let's think about what's going on with this tennis ball for number 10. Number 10, we have a tennis ball of mass 0.060 kilograms and speed of 25 meters per second. So this tennis ball is coming in at 25 meters per second at 45-degree angle to the wall, right? So this is the initial, right? And this is the final. Okay? So here's the initial. And here's final. So it's going in at 25 meters per second. It's bouncing off at 25 meters per second at the same angle, okay? 45 degrees to the wall. They want to know, what is the impulse given to the wall? Well, let's think about what's going on here and break these up into its components. Okay? So initially, right, I have this tennis ball going in at 25 meters per second. Okay? So here, it's initially going in at 25 meters per second. So my momentum initial here is equal to m times v, which is 0.060 times 25. This comes out to, right, 1.5 kilograms meters per second. Well, this initial momentum of the tennis ball going in at 45 degrees can be broken up into its x and y components. All right. So here is my Pix, and here's my Piy. Okay? I'm sorry. This is Piy, sorry. This is Piy. This is Piy. And this is Pix. And this angle here happens to be 45 degrees. So Pix is really nothing more than just Pi times cosine of 45 degrees, right? Which happens to be 1.5 times cosine of 45 degrees. So my Pix is equal to, right? I believe we get positive, right? 1.061 kilograms meters per second exet. So that's the initial momentum in the x direction. Okay? Now, if you look at Piy, Piy is nothing more than Pi times sine of 45 degrees, and that is 1.5 times sine of 45 degrees. And guess what? That's exactly the same value as my x, which is 1.061 kilograms meters per second y hat. So that's my Piy. All right? So here I have my initial momentum broken up into its x and y components. Okay? Now let's take a look at the final momentum. So here's my final momentum, which is this way. So my Pf is equal to m times Vf, right? And my Pf in this case is equal to 0.060 times 25 again. So my Pf is equal to, same as this, which is 1.5 kilograms meters per second. Well, this can also be broken up into its x and y components, right? So here is my Pfx, and here's my Pfy. Right, so here's my Pfy, and here's my Pfx. And this angle here happens to be 45 degrees. Okay? So, what's my Pfy? my PFY is really nothing more than PF times, since this is 45 here, and this is adjacent to my angle 45, is cosine of 45 degrees, which doesn't really matter if it's sine or cosine, because it's 45 degrees, right? So this one comes out to 1.5 times cosine of 45 degrees. And this comes out to same value, which is positive 1.061 kilograms times meters per second. Okay, so that's my PFY. My PFX, however, is in the negative x direction. And you know it's going to be the same value as this, but in the negative direction. So I'm just going to write down negative 1.061 kilograms meters per second x hat. So that's my PFX. Okay? So let's take a look at change in momentum for the x direction. Change in momentum for the x direction is equal to momentum final in the x direction minus the momentum initial in the x direction. Since my momentum final in the x direction is negative 1.061 minus positive 1.061, right? Kilograms meters per second x hat, right? When I add these up, my change in momentum for the x direction comes out to negative 2.122 kilograms meters per second x hat. So it doubles up, actually, in the x component wise. However, if we take a look at the change in momentum for the y direction, right? I have momentum final in y minus the momentum initial in y. The momentum final in y is positive 1.061 minus momentum initial in y is still positive 1.061. So there is no change in momentum in y. This is their same values. So it didn't change at all. This did, right? This went from positive to negative, but this just stayed positive. So what is my change in momentum in the y direction? Good. Like you said, nothing. 0. So there is no change in momentum in y direction. So we have 0 change in momentum. Therefore, what is the change in momentum for the whole system? The change in momentum for the whole system then basically simply comes out to, right, negative 2.122 x hat minus 0 y hat, or plus, you could say if you want to, plus 0 y hat, okay, kilograms times meters per second is what the total change in momentum is. All right. So, I hope you can see how we got that. I'll leave it up there for about a minute so you guys have a chance to copy it down. Any questions? Okay. All right. So let me just fix the attendance for the latecomers. All right. All right. Let's take a look at the last problem. The last problem states here, we have a fullback, right, running at 6 meters per second to the east, right? So we have a fullback. Let's draw a fullback here. Like here. So here's my Eagles fullback, right? Is running with a football. Right? And we have to give him a football. Right? So he's got a football right here. And it's running. I guess we should give him a cleat, Nikes. Give him Nikes cleats so he can run fast. Right. All right, that's my fullback running east. So the mass of the fullback happens to be 115 kilograms, right? That's like a Derek Blunt size, right? And the initial velocity for this fullback happens to be 4.0 meters per second. Okay? Well, we have this tackler, right, coming from the other side now, right? Coming in with, we don't know the speed of this tackler, actually. We just know this tackler is coming in to stop this fullback, right? Right? We don't know the mass of the tackler, right? We don't know the right, speed of the tackler. We just know that tackler stops the fullback. Okay? The contact time between the fullback and the tackler happens to be, right, 0.75 seconds. Okay? Now, this is the initial condition. Final condition is like tackler and the fullback stopped, right? So they stop afterwards. So the VF of the fullback, right, is equal to 0. Okay? And since the initial, so VI is equal to 4.0 meters per second x hat, and it's positive x hat because it's east, right? So that's what we know so far. So they get on head-on tackle by a tackler running due west. And we don't know exactly how fast he's moving. We don't know the mass of the tackler, right? But we do know that he stops him. So calculate A, the original momentum of the fullback. Well, that's pretty easy, right? So for part A, calculate the original momentum. So original momentum initial of the fullback, is simply nothing more than mass of the fullback times the velocity of the fullback initial, right? So it is. Therefore, it is 115 kilograms times positive 4.0 meters per second x hat, right? Therefore, if you work it out, the initial momentum for the fullback is equal to, if you get a calculator and you work this thing out, let's see what we get, right? All right, so 115 times 4, I get 460. So I got 460 kilograms times meters per second x hat, and it is in the positive direction. So this is the original initial momentum for the fullback. All right, what about part B? The impulse exerted on the fullback. Well, if you were to think about how much impulse the fullback, right, gets, is basically change, well, impulse is basically change in momentum, right? And since change in momentum is momentum final minus the momentum initial of the fullback, the impulse then is equal to what we know the fullback final is m fullback times v fullback final minus m fullback times v fullback initial. We already established the fullback's final velocity is 0. Therefore, this whole term just goes to 0 here, minus, right? We already know what this value is, right? I mean, this is already this. So, but we'll still write it down here. Therefore, I get negative 460 kilograms times meters per second x hat. And that makes perfect sense because it has to be acting this way to stop this fullback, right? So change in momentum is in the negative x direction, which makes perfect sense. Okay? Well, what about part C? The impulse exerted on the tackler. Well, how much impulse is exerted on the tackler by the fullback? Well, we know the change in momentum for the tackler has to be negative of the change in momentum of the fullback because it's going in the opposite direction. They have to be the same, right? Therefore, change in momentum for the tackler is equal to negative of negative 460, right, kilograms meters per second x hat. Therefore, the change in momentum for the tackler is equal to positive 460 kilograms meters per second x hat is what we have. And that makes sense, right? That makes sense because if you think about it, if the tackler is going this way and the fullback is applying the change in momentum that way, it has to be in the positive direction. All right, part D. What is the average force exerted on the tackler? Well, the force average is equal to change in momentum, right, of the tackler divided by change in time. We already know how much that is, and that is positive 460 kilograms meters per second, exet. Divide that by delta t, which happens to be 0.75 seconds. So the force average is equal to, right? So if we divide the 460, whoa, I'm running out of batteries here. 460 divided by 0.75, and I get 600, and it's positive. I get positive 613.3 newtons exet. So it's kilograms meters per second squared, which is the same thing as kilograms times acceleration, so that's newtons. Therefore, this is my how much force the tackler feels by the fullback. All right. All right. Any questions? All right. So I'm going to just pretty much end it there for today. I'm just going to go over homework problems. So Friday when we meet, we will actually go over some notes, and we'll have a nice, easy day Friday. If there are no questions, I will end my lecture here. All right.